Hello everyone, my name is Keheliya Gallaba. Thank you very much for attending my talk on RAG engineering. So in this talk, we are going to get an idea about all this different terminology that is related to Retrieval Augmented Generation, that is RAG. And as this theme of the whole event is from zero to hero, we are going to give you a basic understanding about each of these terms, and you can get a brief idea about the whole space, so you can go ahead and then do research later to identify specific components that you need to focus on. And in this talk, I'm going to first talk about why RAG is needed, the overview of RAG, the main concepts, and some advanced retrieval concepts, advanced RAG patterns, applications of RAG in software engineering, limitations of RAG, and productionizing challenges of RAG. But as we've seen in yesterday's poster session or the lightning talks, most of you already know about these RAG concepts as you explained them. But I'm going to go from basics, so please bear with me if you know these details already. So we know foundation models have shown potential in many domains, as you can see. So even though foundation, for example, the language models has been created first to do next token prediction, it has been used in other different areas, such as medical consultation. For example, you can ask a foundation model based system about medical problems, about the symptoms, and about diagnosis. And there's this work called ChemCro that is about chemical synthesis. You can that tool can read through relevant literature in chemistry and design experiments, conduct them, and write their findings. And then there's molecule discovery, that is coming up with new molecules. And then there's finance domain also. People have been using it for predicting financial tasks, generating financial related news. And then of course there's legal services. That is about getting consultancy about legal matters. So these are very diverse domains that is not directly related to next token prediction. So with this technology being applied in different domains like this, it introduced some challenges. So as I said, there are some limitations hindering the foundation model's usefulness. Let me go through some of them here. So first thing is outdated knowledge. Here in this example, they're asking a question about the 2024 Olympics, but the model has been trained, the knowledge cutoff was in December 2023, so it couldn't give an answer. And then lack of domain specific knowledge. So this doctor is asking a specific question about a blood pressure for a certain age group. The model don't know the exact details about this domain. Model may not have pre-trained using this information. And then there's the lack of internal data. So in your organization, if you are trying to use foundation models for your own internal business use case, it may not have an idea about the internal things about your company. If you're using an OpenAI model, if you ask it, who's handling this thing in my company, the model will not know because it doesn't have the access to these private databases. So, but the thing is, foundational models have this problem of not saying I don't know. So most likely it will generate something. People use the term hallucinations, confabulations, different terms. They try to come up with plausible sounding answers for these type of questions. So retrieval augmented generation has been proposed as a solution for this type of problems. Let's go through that idea briefly. So so usually you provide a question or an input query to the foundational model and it gives you an answer. But retrieval augmented generation adds this additional step called retrieval, where you can use a knowledge base to retrieve some information, and then there are some additions on top of that. You can do fancy stuff like pre-processing and post-processing. And but this retrieval and doing the generation based on this retrieved information is the core idea behind retrieval augmented generation. So you use a knowledge base to get some facts relevant to the user's query, and you prompt that to the foundational model and return the answer back. But people found out sometimes it's not working very well, so added these steps, that is for pre-processing the query before doing the retrieval, and post-processing, that is the results returned from the model, retrieval. So these components are optional. So basically the key idea behind RAG is the augmenting foundation model's knowledge with appropriate facts from a knowledge base to enable grounded generation. So the key idea here is grounded. So what's grounding in language models? So the key idea is every claim in the response generated by the LLM can be attributed to a document in the knowledge base. But retrieval augmented generation, or RAG, is not the only way of doing grounding. There are many other techniques such as constraint decoding, guardrails, there's another fancier one called corroborate and revise, and then corpus tuning. So these are the alternatives. And there's a key differentiation between grounding and factuality. Grounding is attributing to a user-specific knowledge base, like can we connect this claim to the information that is in the knowledge base. Factuality is about attribution to commonly agreed world knowledge. So the stuff that we already know about the world, the facts about the world, adhering to those, attribution to those, we call it factuality. But grounding, we refer to them like the user-specified knowledge base. And then now I'll go explain a little bit about pre-processing. So here the pre-processing, there can be several tasks like query rewriting. That is like you reword the query for query before feeding into retrieval, and then the query decomposition, query expansion. And in the post-processing section, there's like re-ranking of the results, compression of the results, and correction. I'll go into more details about this stuff later, why these are necessary, but that's the whole idea. So now let's go into the retrieval section. So retrieval section can be divided into two main parts: dense retrieval versus sparse retrieval. So idea behind the sparse retrieval is you use an encoding. You can think of it as like an lexical representation. So so you use some exact similarities between the query and the document. So here what happens is, so in the database you have the chunked or tokenized documents, and then you have indexing, and when the query comes in, you do a relevance score computation and then retrieve the results or chunks. So you can use techniques like TF, IDF, or a BM25 that is already known in this space, that came before these large language models became a thing. But dense retrievers are about using the semantic similarity, where you have a encoding, we call them embedding, that we use for the documents and also for the query, that captures the semantic idea, semantic semantic similarity. And then we do a relevance matching like the cosine score. Yeah, so now let's go into the details of each of these. So as I said, the lexical approach, the most common ones are TF-IDF and BM25. In the TF-IDF, where we consider what the basic idea is, how important a word is in to a document in a collection. That is, this is the formula for computing the TF-IDF. And BM25 improves on that a little bit. So the idea here is, so the weakness was of TF-IDF was, so if the document was longer, it was more likely to say it's similar. So BM25 takes into account the length of the document and applying a saturation function to accommodate that. But the good thing about these lexical approaches is they don't need fine tuning. And they are really good for exact term matching. So for example, in technical documentation, you have some unique identifiers like this error code or the issue identifier. So if you are looking for that exact match, this type of approaches will be useful. But since it's lack semantic understanding, it will fail to capture the similarity between similar concepts like the synonyms, for example. Now we move. I forgot to mention one thing about this lexical approach. So why do we call this sparse retrieval? So when we build the vector for this sparse techniques, we get a very long vector that has a lot of zeros in it, and in some places you have values. So that's why we call them sparse, opposed to dense one that we have shorter vectors that has lot of values without much zeros. That's how the term came, sparse retrieval and the dense retrieval, like because of the vectors, sparse vectors and the dense vectors. And then let's before going to the dense retrieval, I want to give a brief introduction to what are embeddings. So embeddings is a way of representing data as points in space, like a multidimensional vector space. But the cool thing about plotting them in this multidimensional vector space is semantically similar stuff will appear together. And you can do certain operations on that and like get results. For example, you can like deduct. So in the third plot, you can see the countries and capitals are appearing in this space, and so certain countries and their capitals appear closer together, and you can do clever operations on this, like you can divide Turkey from, you can deduct Turkey from Ankara and add Canada to it, and you'll get Ottawa. Things like that to build relationships between these things. And then what we are, so to plot this vector space, what we are doing is we get a sentence and we convert it to a bunch of numbers, what we call a vector. And we try to, for a given query, we try to check how one vector is close to the other vector. That we use techniques like cosine similarity. And another key point is these embeddings are deterministic, unlike the inference models where with every iteration you get a different result. These ones will always generate the same output for a given set of inputs. So if you're coming from a software engineering background, you can think of it as like a hash, but it's because it's a form of compression, you will lose some information, but it can retain some semantic information. So one of the earlier work that introduced this, that became popular, that popularized this concept was Word2Vec from Google. And then there came the clip model from OpenAI that could do this for image and text data on the same space, same embedding space. And then there are all the other newer approaches like BERT, Instructor XL, ADA 002, and sentence transformers. There's a website that you can go to check all these. It's basically a leaderboard. You can see which ones are performing better these days, because it's rapidly getting updated. So you may find different ones recently. So based on this idea of embeddings, we do retrieval. That's what we call dense retrieval. So there are several techniques of doing dense retrieval. Dense passage retrieval, also called DPR, is one such thing that came earlier. So the idea here is you have two different encoders, like they used BERT encoders in the paper. So you encode the questions using one model, like in this case the inventor of the compiler, that gives you the question vector, dense question vector, and then you encode the passages also that may have the answer for this, and for that you use a passage encoder and you get a dense passage vector. And to check the similarity, you use the inner product similarity or dot product similarity. This has been shown to perform well for open domain question answering, where like you ask an open question about things like this, like general knowledge, and it performed well. And I wanted to show another thing about this. About in the training process, they include the irrelevant passages also in this. That is also another important thing I wanted to highlight. As you can see in the bottom right corner, you can see the question, relevant passage, and irrelevant passages that will improve with the training. So as you can see, this approach needed multiple encoders and also required a lot of training, the pre-training. So it may not be, it was popular, but it was, there were many improvements that came later. So Contriever came up as an alternative. So the key idea here is you don't use two encoders. You use only same BERT encoder for encoding queries and the documents. You first have to chunk or tokenize the documents and do the encoding and put them in the database. And then you do a relevance scoring. When a query comes in, you compute the similarity and get the retrieved documents. Here also we use the inner product similarity. As you can see on the right side, it achieved very good results. Then came the another dense retrieval solution is Spider. The key idea there is they do span-based unsupervised dense retrieval. So the key idea is here the spans are like tokens that are appearing closer together. So the intuition is, so they use most commonly occurring spans like this and use that to come up with positive passages and negative passages. So in this case, they have a span called the priest stood for himself and his male descendants, and in the good example that span is appearing, and in the bad example that is not appearing. So they use this data for the pre-training. And the key thing I wanted to highlight here is in this one also, we didn't, it's like an unsupervised way of training. This one was a supervised approach, so you need like a lot of label data for this, but this is an unsupervised one, and this one is also unsupervised. But all these unsupervised techniques, they use something called contrastive learning. Contrastive learning, the idea there is, so you don't need as much as like label data. You show two examples to the model that are different. It's basically, we don't have to explain this is this type and this is the other type. We provide these two examples, and model learns using this contrast. So this technique also uses contrastive learning, and it has shown good performance to this open domain question answering. So as I said, two key ideas here is this span idea. Like if we can use this recurring spans, repeating spans, we can do a good job of training the model to retrieve relevant information. And then the composition of these large text into these passages, because passages, if you think about them, we separate large text into passages because we want to have same ideas like grouped together. So they use this inherent structure called like the passage that is in natural language to do a better job of retrieval. And now you may be wondering, we talked about retrieval, what happens after we retrieve that information? So there's a whole bunch of papers about proposing different approaches of doing this integration, because you have to retrieve this from, like you do a semantic similarity search and you retrieve some information. You need to integrate that into the query in certain way, and then only you can use it for getting the final output that we should send to the user. So there are 4 different patterns here. I'm going to go each of them. So first is the input layer integration, or called query-based RAG. This is pretty simple idea where you retrieve the information, combine it with the query, and feed it to the generator and get a result. So there are multiple examples of this here. And then there's the intermediate layer integration, or also known as the latent representation based RAG, where you integrate the retrieved information while you are doing the generation. Next, the tokens are being generated, you integrate the retrieved information. And then there's the output layer integration, where you at the very final layer, once the token probabilities are generated, you try to combine these with the retrieved information somehow and present it back to the user. We call them output layer or logic-based RAG. And then there's another approach called speculative RAG that is also kind of similar to the last one, but there are slight difference here, because we are generating tokens and continuing the sentence using the retrieved ones. So we call them speculative RAG. I'll go into the some of the details here, for each of these sections. So first one is the input layer integration. The most common, the one is rel. Before that, key thing I wanted to point out here is, as you can see, for some of these techniques, you can keep the generator frozen. You don't need to mess with the generator. You can combine the retrieved information before or after the things are, the foundational model does its job. But there are other approaches like the intermediate layer integration, where you need to mess with the internals of the model to come up with the next token based on the retrieved information. So this has a lot of application differences, as you can imagine. Some of these are easier to use for ourselves, but some of them needs a lot of infrastructure to train the model to have this. Realm is one example for input layer integration, where we use a knowledge retriever to get the relevant examples from the knowledge corpus, and then there's a knowledge augmented encoder. So these two things, we are doing an unsupervised pre-training and a supervised fine-tuning for achieving all these things, both of these things. And next we have the intermediate layer integration. Retro is one such example, where they call it a retrieval enhanced autoregressive language model. So it's part of the language model. In the intermediate layers, we use the retrieved information. And then there's the output layer integration. One example is k nearest neighbor, KNN-LM. So the idea here is, so in the final layer, you have probabilities for the next token or next word. Then you have the retrieved tokens also. You use the k nearest neighbor algorithm to merge these things to come up with the most suitable next word. So they claim this approach can be applied to any neural language model. And as I said, the idea is combining retrieved probabilities and predicted ones in generation. So the speculative RAG, the example is coming from this copy is all you need paper. So think of it as like copy paste. So here, when the model predicted the sentence part, the Dune film was released, the retrieval completed the rest of the sentence with these sections, like the when it is appearing in the theaters, all these things. So it is like working together with the generation to complete the sentence. That is why it's slightly different from the output layer integration. And that is about the retrieval. Now let's go into a little bit detail about pre-processing. So as I said earlier, in pre-processing there can be multiple things happening: query rewriting, query decomposition, and query expansion. So the basic idea there is the question that the user asks may not be the best representation that we should use to query information, to query examples that is in the knowledge base. So we do something and reformulate the question, or edit the question, or edit the query, so it will do a better job of retrieval. So I'm going to explain this one of these techniques called hypothetical document embeddings, because I think it's like a very cool thing that they did. So the idea here is, so you have questions, and we think there are answers in the knowledge base for these questions, but using that exact query will not be good. So what they do is, using that question, they generate some hypothetical documents. As you know, the model can hallucinate, and it has wrong answers, but it doesn't matter. So what they are going to do is use these generated documents to query the knowledge base. So their intuition is using these hypothetical documents will give better results than using the question to query. So here, as you can see, the question is about how long does it take to remove wisdom tooth, and there are generated documents. It usually takes between 30 minutes and 2 hours to remove a wisdom tooth. But this may be inaccurate, but it's okay, because the idea is when you retrieve, it will have correct information. What we want to get is a closer match. So here they have shown, by using this example, the fake document generation using GPT gives better performance. And the other key thing here is they use the contriever to do the retrieval. This is one of the things that we discussed earlier, retrieval techniques that we talked about earlier. And then let's talk about post-processing. So post-processing, we can do multiple things like re-ranking, compression, or correction. First, let's see why we need to do re-ranking. So here, in the very first example, you can see as the context, it has provided 7 documents to the language model. So in the retrieval phase, it got 7 documents, and it gave it to the language model to use this information. But it has been observed when you have too much information like this, the model may not use this information ideally. So this phenomenon is called lost in the middle. I'll go into the details of that also later. But then there's the opposite problem. When there's too little content, you are likely to miss the optimal one. So in this case, the optimal answer is 1. But because you retrieved only the top 3, you missed the optimal answer, that is 1. So re-ranking, the idea here is you reorder the results using this re-ranking. So when we have limited context, we can have better results. So that is the intuition. So one popular way of doing re-ranking is doing cross-encoders. Now, what is this term cross-encoder? Don't worry, this is 0 to hero, so I'll explain this also. So usually they, as we saw earlier, what happens is they use two encoders for encoding documents and queries, and then you do a similarity score. So what this means is only at the so at the inference time, you do the encoding for the query and do the cosine similarity and get some results. But in the cross encoder, what they do is they take the documents and query both together and encode them and they can encode across they can build relationships between tokens also, and this can give better results. But as you can understand, this is a very, very costly thing. So the basic idea here is you use when the query is coming in, you do the retrieval using by encoding, and then you have some retrieved candidates. So because the by encoding is used to retrieve the information, we don't get that cost problem here. But when it is we have narrowed down our results to 10 results now, then we do the cross encoding. So since we only have 10 retrieved documents, we can easily do the cross encoding and this re-ranking. So but if we had to do this cross encoding with the query and all the documents, it will be very costly. But we don't have to do that now because we only have a subset of documents that is retrieved, and this allows us to rank everything based on the rank the retrieved documents using the similarity score and pick top 3 or top 4 results. This is called re-ranking using cross encoders. And then there's another technique called refiner, restructure retrieved content, that is also a post-retrieval technique. So key idea here also, we when we retrieve the information, we reorder it based on some metric as I explained earlier, and rewrite some of the sentences. So at the generation phase, it can do a better job of generating the correct answer. So it has not only the limiting it to a certain set of results, it does some rewriting also. So that's why they call it refiner. So now what we are here at the we completed the overview section. Now let's move on to the advanced retrieval concepts. So this is because people figured out the basic retrieval may not work for certain scenarios, so they need some advanced advanced techniques. Okay, so I'm going to talk about this technique called SPLADE, that is sparse, lexical, and expansion. So we already know the keywords related to this. So we learned about the sparse representations and dense representations. Both of them have limitations. What if we can merge these things together, and we can get and we get the best things from both of these worlds and do the retrieval in this hybrid way. So the key limitation that we talked about in the sparse lexical approach is the key, technical terms the word needs to be exact. So it has some trouble with the synonyms and stuff. So what they do is they do expansion of these terms. For example, here for large monkeys, they expand it to have different terms like orangutans, great apes, gorillas. So it can get rid of the limitations of the purely lexical approach. So then they combine these two approach and they claim to solve the vocabulary mismatch problem. So that is basically the idea behind SPLADE. And then there's another advanced retrieval technique called ColBERT. That is also a combination between sparse retrieval, dense retrieval, and re-ranking methods. So they call this a multi-vector representation because you have, in previous dense retrieval approaches, you do the embeddings for like the chunks of the text, but here instead of doing that, they have like token level vectors, and then in the when you do the embedding of them together, they use this token level information to do the retrieval. But as you already know, this can be very, very costly because you have to keep information about token embeddings of the documents and also the token embeddings of the query. So they have some strategies to save storage like downcasting layer, aggressive quantization, and pooling. And they use the maxim operator here to come up with one value from all of these token relationships, and they show they have a better retrieval than all the previous techniques. So then there's a very recent one called ColBERT, that is a combination of multi-vector, like they combine the multi-vector approach that we discussed earlier into multimodal. So here, this is also very interesting. What they do is they not only for text tokens, they can do the same approach for text and image and other different modalities also, and they do this late interaction that we talked about earlier. At the inference time, you use the combination of the query and the documents embeddings to retrieve results. This can get some very interesting results to answer questions about multimodal things. So here, because it can capture semantic information about the images and the text both, it gives you some interesting results. So here it can answer questions about this graph, for example. Here they ask the question, which hour of the day had the highest overall electricity generation in 2019? With the way they embed this information using this multi-vector and multimodal technique, you can answer questions like this from this. Okay. Now let's go into the advanced RAG patterns. So what people found out was, adding these advanced techniques for retrieval only will not solve things. So you need to do more crazy things for this whole system, and they came up with these different patterns. You can also use the term cognitive architectures for this, but I don't go into details about cognitive architectures today. We have a session about agents tomorrow. We can learn about cognitive architectures in detail there. But basically the idea is how you combine RAG concept with all the other developments in this area to build an end-to-end thing that have higher performance. So the key idea here, so I'm going to explain the technique called contextual retrieval. This is a very simple idea that was recently popularized by Anthropic. So the idea here is, so user's question is about this particular corporation, but due to the way that we had broken the text into chunks and created embeddings for them, this retrieved chunk doesn't have any information about this particular corporation. It just says the company's revenue grew by blah. It doesn't say which company. So what they propose is before creating embeddings for these chunks in our documentation, what if we have some surrounding context wrapping around these sentences or chunks to give more information. For example, here you can see in the contextualized chunk, they have added information. Okay, this is coming from this SEC filing. This is about Acme Corporation's performance, and this is coming from this year. Things like that. So they show having this wrap around improves things. Like prepending chunk specific this context to each chunk before embedding will help. But you cannot assign someone to add these extra sentences to the chunks, so they used a language model to come up with the relevant context first, surrounding context before embedding them. But they didn't stop there. They integrated this technique in an end-to-end pipeline and showed they get improved results. For example, first at the pre-processing stage, they have all of these documents and that for a certain domain. Then they created the chunks, and for each chunk they run a prompt to gather the relevant context, and they get a new chunk that has the context surrounding it, and then they use the embedding model to create embeddings. But as we already saw, only the dense retrieval is not ideal. For some of the cases you need dense retrieval. For some of the cases you need sparse, because if you have like technical terms or some jargon that you need an exact match, so you need that approach also. So they have a hybrid approach that they use a vector database and also this TF-IDF index. So they get better results by combining these two approaches. They don't stop there. They do re-ranking also, and then they show re-ranking optimizes retrieval. So re-ranking we just learned few slides ago. This helps when you have too many number of examples. You can filter them out into a subset, and you can first re-rank from these retrieved examples and only select the top ranked ones to get better performance. So this is so in the contextual retrieval article they explain this whole end-to-end process. Then there's this another technique called self-reflective RAG or self-RAG. So the intuition here is, so there's a certain query. For example, here in this case it is how did US states get their names. So they retrieve different documents from the vector database, multiple examples, and then they have then there's a critique model that critiques all these different retrieved cases based on different conditions, whether it's like helping the answer, like it's using a language model to critique the retrieved examples basically. So it's checking different things, whether this retrieved information answers the question, or whether it has all the supported claims that need to be supported are being supported from these examples, and select the suitable ones. So for this one, they call it self-reflective RAG, because this whole system reflects on the output to come up with the completions. And then there's another technique called least to most prompting. The idea here is you have a query, and to answer that query you may first need to answer some smaller sub questions. So for that it uses a language model to decompose the query and use RAG to retrieve examples for each of the you basically try to answer each of the questions separately using RAG. So you first prompt it to get relevant documents for the first question, answer that, and the second question use RAG to answer that likewise, and then you use the whole generated answers for all the generated sub questions to give an answer for the final one. So IRCOT, that is also very similar to this. It uses retrieval with chain of thought reasoning. So chain of thought reasoning is a complex concept that we are going to talk about tomorrow also, and also in the prompting you may have covered this idea. So here the idea is you help the thought process or the chain of thought using the retrieved answers in each of the steps. So you have an initial question and you retrieve some information, try to come up with a reason, and then you have another sub question that you need to answer. You have a chain that you need to invoke to get to the final answer. Okay. Then the next concept is graphs. So we talked about text and images, but then graphs are also another data representation that we have a lot of data in the wild. So how can we use the structures that we already have in graphs to answer natural language questions? So I'm going to present here two works, one from Google and one from Microsoft. So what Google paper presents is how can we encode this graph related information in the textual form for such that the language models can answer questions related to graphs. So here they in their example they have an example that's explaining about a family tree, the relationship between family members of a royal family, and then the question is like, who will be the next leader based on these relationships? How can you infer the answer for this question? So they experimented with different encoding formats to represent this information as text. So the graph can be, they use the adjacency format, incident format, and the friendship network to encode, and they tried out different graph related queries on that, and they found out most of the time language models struggle with that type of information that is encoded as text, the graph information text encoded as text, but in general incident encoding approach gave some good results. And then Microsoft has released this framework or the library called GraphRag that is that can be used to answer graph related questions because there's a lot of graph related information in the commercial domain also. So what they what they have is some libraries for indexing this information. So how can we extract entities, relationships, and claims from text and put them into like a graph database, for example, and also doing like community detection, community summaries, and then like using this graph, use the graph vector space to store the graph relationships, and the textual vector space to store the textual information. And then they have two techniques for querying this. They call it global search and the local search. Global search is about how can you answer like general questions about this the community, like the set of graphs you have. And then the local search is about how can you answer specific questions about nodes, a particular node and a particular edge, specific questions like that. So they propose an infrastructure. You can efficiently index this information and query this information. You can check it out if you have some graph related problems that you want to solve using RAG. So that is the basic concepts of RAG I wanted to cover. Now I move on to the applications of RAG. So first example I want to show is the code generation. So in this paper that was presented in ICSE this year, they use RAG for code generation. So code generation is basically you use a foundational model to you have part of the code, you want to complete the rest of the code, like the GitHub Copilot. So they show using RAG to store code examples like similar code, and applying RAG here you can improve the code generation performance. So this retriever uses queries in natural language and also code to find similar code, and it increases the code generation performance. The next one is about code completion. So they are also so they use the repo. So their approach called repo coder is also using RAG to complete certain parts of the code. So you have so they demonstrate if you don't have if you don't have RAG, the performance is not good, and then they use a primary version of RAG that use code examples retrieved from a vector database, and then they do iteration on this. They have multiple iterations on this retrieval to come up with better performance for the completion of the code. And then there's the automated program repair domain. So automated program repair, the basic task here is you have so you have a failing test case, and you need to generate the code that can make the test pass. Basically, you need to repair the program in a way that the test case can be passed. So for that particular domain also, they have shown using the RAG approach, using examples stored in a vector database, you can get better performance. And for code summarization also, people have shown RAG can be useful. For this paper, I think one of the authors of this paper is Prem. He can give more details about this work. So it's also for code summarization task, the use of RAG. So then now let's move on to the limitations of RAG. So as any approach, RAG also has some limitations. So more and more models are supporting a large context size these days. So you can provide a lot of examples or a lot of related answers when you use RAG to a generative model. If you have some estimates, for example, if it is around 5,000 tokens, it will be about few pages of text. If it is 5,000 to 25,000, it will be like a book chapter, and then there can be like even a whole book. Like there are models that they support like several books, like several thousand books even in their context. But what people observed is if you have this type of very large context provided to the foundational model, foundational model had trouble answering some so for answering a certain question, if you wanted some information that's hidden inside this longer context, it had some trouble. So when the context was getting increased, it had some bad performance for answering these specific questions. So this brings us to the problem of like trimming the context that is needed to provide it to the generative model for the generation step. So you cannot like retrieve all the information or like all the examples. You need to trim that down into the most important or most relevant ones and provide it to the generative step. So that's why all these, as we discussed earlier, these re-ranking steps are necessary. Re-ranking or filtering or some steps like this are necessary. And this is also another closer concept called irrelevant context. So the example that I have on the bottom right shows like if you provide model with some unnecessary information that is not needed to answer this question, it will give you some wrong answers. So in this particular case, they include like the monthly rent information in the question that is not needed to answer the question about the bank balance, but the model decides to deduct that information. So this shows you have to always be careful about what you include in the context. So people may think, oh, now there are better models that claim to do reasoning, like the OpenAI's O1 model. Oh, it can figure out all these things. I don't have to worry about the context that I provide to the O1 model. But even in that OpenAI documentation, it specifically says limit additional context when you are working with RAG with our O1 model, because it can go haywire if you give it unnecessary information. So this shows this filtering or re-ranking steps are even necessary even with these newer models that are coming up. This is not becoming irrelevant. So on the left hand side, I have another example that is similar to O1. So Cognition is the company behind Devin, the automated software engineer. So they also did some experiments with O1 for software engineering tasks. They also noticed if you have like unnecessary tokens and redundancy involved, it negatively affected performance. So RAG is not a solution for everything, and you have to be very careful how you use this tool to work with models. You have to do careful context management, even with these newer models. Okay, and then this brings me to the final stage of this presentation, that is the productionizing challenges. So, so you may be wondering, so there's all this terminology out there. You can do prompt engineering. We just had a session about prompt engineering. You can do RAG. So, like we just learned about right now, and then you can do fine tuning, or you can do pre-training from scratch. So which way should I go for my particular problem? Which one should I choose? So there are several things that you have to think about, like the cost and data that you have around. So prompt engineering you can use if you have several examples. You can like do like few shot prompting, and just embed these few examples that you have in the prompt and provide it to the generative model. But if you have like a large knowledge base, you can try with retrieval augmented generation, because it's a relatively low cost approach, because you don't need to do model training, you don't need the infrastructure to do model training. You just need to have like hundreds or thousands of examples, and you just need to retrieve the correct relevant information and feed it to the model. But if RAG may not solve the problem for you in some cases. If you want to do certain specific tasks, like for example, programming language translation, like code-based migration, things like that, you may not find good results with RAG. Then in that case, you may need to fine-tune your model to have to speak a certain language, like in coding terms, to speak output certain answers in a certain way, while keeping the capabilities of the original model. So you are not doing something from scratch. So you get a model, you just need to add some additional capabilities for that model. So in that case, you can do fine tuning, but for that also you need a lot of example, way more than RAG, and you need infrastructure to do this fine tuning also. But pre-train from scratch is a whole different thing, that you need to have like brand new capabilities that are not that is not visible in the current models. That so you may have to use a lot of data out there to pre-train a model from scratch. So based on your use case and based on your capabilities, you can try to go step by step, like to check if these approaches are giving you good results. And then, as you can feel from the previous steps in the presentation, there are so many steps to configure in this whole pipeline. So in this case, you first have to get you have to first find the knowledge base, and then you have to do chunking. Chunking is like you have to split into ideal pieces of information for creating embeddings. So based on your application, it could be sentence level, passage level, or token level. Like you have to think about the chunking method, and then you have to think about what is the most suitable embedding model for this. What model is most applicable for this use case, and then you have to think about the vector database to use. There are different vector databases being offered right now. You have to think about which one to use. So that reminded me, I didn't really introduce vector databases, but the idea, you can think I didn't introduce that intentionally, because the whole idea of vector database is, once you have the these embeddings or the dense retrieval approach, you have to retrieve these things, retrieve these embeddings very efficiently to do the similarity. So vector database is, you can think of it as a layer on top of these embeddings that you have that allows you to efficiently search. So you have a lot of cool tricks like different indexing techniques from the database world applied in the vector database to specifically query for vectors. So this is something closely related with embeddings, but these search algorithms are different. They have their own like search indexing and searching algorithms. Then we have to think about what vector database to use also. And as we said, we have to like select the certain set of examples. Then we have to do like, there are a lot of retrieval techniques. You can retrieve use one of those to retrieve, and then you have to do re-ranking, which one to do for re-ranking, and then you can do other fancier stuff like contextual retrieval, where you add some more details before embedding and storing them in the vector database. And then there's prompt compression, prompt engineering. As Felipe explained, you can tweak the prompt also to work with the retrieval task. So there are a lot of knobs. So it's very complex. So on the right side, I have shown several places that you have multiple options. So it becomes a very, very complex things because you have too many knobs to tweak. So there could be certain approaches that we can get help from for this. So in software engineering, there's this continuous experimentation idea. You can introduce certain flags and see how the performance change over time. So we can use techniques like this to gradually introduce these changes. You can keep one thing frozen at a time and then change things to come up with the optimal solution. And then we can do automated pipeline optimization. So we give all these options to a optimizer and come up with the ideal one. So I recently saw this work called AutoRag. What they claim to do is they help you to select the combination of these different things that to come up with the most optimal configurations. Yeah. And then we come to the big thing in the room about evaluating these systems. As you already know, evaluating foundational models are complex in itself. But now when we add this RAG system, when you put together the RAG system in place, it's a whole different beast. You have to think about how to evaluate the whole RAG system. So if you think about it, there are multiple places you have to evaluate. You have to, of course, if the final output is not good, we have to fix a certain thing. But the problem could be anywhere. You have to evaluate the embeddings. You have to evaluate the retrieval from the vector database. Then you give this to a foundational model. So when you combine this retrieved information to at the generation phase, you may, like, even though you give it the ideal examples, it may not do a good job because you had a bad prompt, or for that particular type of question you didn't need that information. So there are there are multiple places you need to evaluate. And then you have to, of course, evaluate the final result also. So to help with this, there are many approaches that are coming up. So RAGAS is one framework that they propose to use these different metrics for evaluating your whole RAG pipeline. They have concept from information retrieval that has been studied for decades. That's about retrieving the correct information. But also they have some foundational model specific metrics also. So it will be worthwhile to look into this type of frameworks to evaluate your RAG system. But the key thing I wanted to raise here is so your problem and your data is unique to you. So all these RAG techniques or all the data sets that they have out there may not be suitable for using off the shelf for your application. So you may need to have your own evaluation set with your own data and own queries for evaluating things. But there are libraries that they are out there, RAGAS, and there are another Python library also that has this metrics built in, so you can reuse these pieces as necessary and build your thing. So since I have some more time, I wanted to explain another thing I forgot to mention in the previous slides. So so you may be wondering, oh, there's all these pieces. As I said earlier, there are a lot of components here. Do I have to do everything by myself? Do I have to implement all these steps in Python? So there are libraries out there like Llama Index that has different integrations for these different type of libraries and different type of databases, different type of re-ranking or ranking solutions that you can integrate together, so you don't have to implement that on your own. And then at Huawei also we are also building our own platform that can help people build foundation model based applications. So we are also introducing features related to RAG that you can use in your end-to-end RAG pipeline to build RAG pipelines easily and evaluate things easily in that space. So I have a bunch of survey papers here listed on here. So once I share the slides, you can go through this information. So as I explained to you, this is a very broad category. I just wanted to give you some taste of what's out there. You can read through these papers and follow along if you are interested. And for me, I'm very grateful for all these survey papers that helped me to build this slide deck also. And also I got a lot of information from the blogs and papers out there. I am thankful for those also. I have put the links to this blog post as relevant in the slides also. Once we share the slides, you can follow through this information and get more information. So that takes me to the end of the presentation. If you have any questions, you can ask me now.
Thank you, Keheliya. Thank you, Keheliya, for a nice talk. Like, we're open for questions.
I have a very quick, hopefully, question. So the RAG is really to add domain knowledge that's perhaps not visible to the model, one of the main kind of purposes, right? So some of the tokens might not be visible to the domain models, to the general models as well. So from all this description, I haven't kind of found the way how you're going to expose these tokens so that actually general purpose model would be able to reason about those, or maybe I missed something. Does my question actually make sense?
I didn't actually get your question.
So RAG is for exposing some domain that general purpose models don't know, right?
Yeah.
That domain may have technical terms, keywords that are not visible because they're private, they within the company firewalls, right? That are not visible to the general purpose models. Now, which parts of this pipeline would translate these technical terms in such a way that the query is processed, is being able to be processed by general purpose models?
So I think there are two pieces in your question. So one thing is, yes, so the whole purpose of RAG is providing this context to the language model. So we use this vector database to store all of our examples or some code, and we have some retrieval thing to retrieve these relevant examples relevant for this query. So by rephrasing the query or re-ranking, we can improve this retrieval. But after we retrieve, what we do is we integrate that with whatever was generated from the language model. So as I said earlier, there are multiple places you can do this integration. So you can either you can ask the generative model the same question, the bigger model the same question, and while the tokens are being generated, you can integrate the tokens that you retrieve from the vector database. Or you can integrate the retrieved examples to the query and provide this whole context into the generative model as part of the prompt. So this gives us the chance to expose the model to these unseen examples. That's the point.
Yeah, I got that totally.
Yeah.
The only thing that I didn't get is, suppose we have a department name that's
Yeah.
general, right?
Yeah.
Or error code that's not seen ever by the general purpose model,
Yes.
right? So what you're saying is use TF-IDF or embedding to translate that error code into something else, which then is meaningful for the model to ask, and then once you get the data back, then you translate it back into, map it back into that particular error code, just to be very specific.
No. But what I'm saying is, so these two retrieval techniques, the dense retrieval and sparse retrieval, these are they have their own strengths and weaknesses for retrieval purpose. So what we are doing is, so when a user asks a question, so if the user's question is about a specific error code, in certain cases you may need all the surrounding error codes also, that is very similar to that. For that type of thing, you can use dense retrieval. But if you need some specific, like that error code related knowledge to answer this question, you can use sparse retrieval, or you can use a combination of both. But so what we are talking about here is getting this, retrieving these, using these embeddings, retrieving these from the knowledge base, so we can enhance the prompt that we are providing to the generative model. So by doing this RAG, so you said you used the term understanding. So we are not giving any understanding capabilities to the generative model. So basically what we are saying is, so this is the query that user asked. These are some explanations that may help you to answer that question from the documentation or from issue reports or whatever. Use this information as necessary to answer that question. So you with the weights that the model already has, it may know about fixing bugs in general, but not this specific bug. Then it uses the documentation example to give a certain thing. So for example, so there are like large language models may know about most commonly used programming languages, like most commonly used programming languages in public, like Python and JavaScript and things like that. But we may have like our own esoteric programming language, but it doesn't know the generative model doesn't know the specific syntax of this model. But because it has seen all these different type of programming languages like functional programming languages and all these other type of programming paradigms, it may it can give you a general solution. But because it doesn't know the syntax for our own language, it cannot give you a good answer. So basically what we are helping with these examples is to ground the whatever the knowledge that model has with our context. So our context is this esoteric programming language that we made up. Try to use your programming knowledge to come up with a sample program in this language. I just used it as an example, but did that answer your question? Or?
No, I think it did, but my question was, the token is still not going to be there, so you're basically providing these examples and asking the generic model to summarize, please summarize in short these examples with this.
Yes.
And then it does.
Yes.
Basically what it
Yes, yes, yes. And like because it has been already shown in foundation models, it can generalize to unseen examples. So you don't have to have the tokens in your weights. Yeah.
Sorry. So it's not really a question, but what I'm saying is that when we talk about you gave it a document, you want to know, or maybe this document is helpful, but which part of it is helpful, right? And maybe some part of it, the language models can leverage that part. But isn't it that I think, so there's a concept called monosemanticity, which means a neuron is directly mapping to a feature, one-to-one relationship, very simple, linear system, right? But now these models, it's not semantic systems. So if we don't know at the token level how to map these features, it's not a linear model. So even at the model level, we don't know how the mapping is. Then how we are building a RAG system, I know in this document, in this book, which part of the book the language model really understand. So I'm thinking, would that be like non-linear system kind of field that actually maybe trying to solve it in the other way? Because I feel if we just look, oh, maybe this part of the document is good, we do needle in the haystack. But it's not a linear system. How can we make sure this path is working? It's not really a problem, but I'm just stuck at this thing.
Yeah, I think like all of us are, right? Like we are trying to understand how this system works, right? And we are like poking at this thing and coming up with these different hacks. I would say like, oh, along the way, we are figuring out how to provide larger context. And then only we are realizing when you provide large context, some of the information that's in the middle may get lost. The model may, so the thing that I didn't go into details, in that paper they explain, so if you have larger context, some part of the, like if you have the information in certain parts of the text, it can answer better. So in the, it says if it is in the middle, it cannot answer. It doesn't do a good job. only at the beginning or the end it will relevantly answer. So these type of behaviors that we are only observing right now with the model capabilities are growing, right? So yeah, like I share your concern that we may not be able to solve these problems with these current approaches, but it's like we are trying, right? Like does anyone else have like some comments about this?
Okay, so it kind of follow up from the first question, but more practically into inferred versus grounded truth. We know the language models have seen, let's say, the materials or documents from some period to a certain period. Then RAG comes in to augment the model from new data. But when we look into, I'll just give a case, an example, let's say the United States. If you look in all legal documents, the Constitution, the preamble, whatever legal document you have in the United States, you will not see the word democracy written down. But people know America is a democracy. So if we base on this truth, the language model will not know America is a democracy. But through inference, it will use a principle of democracy to address America as a democracy. Are you getting what I'm coming at? Now, if we look at augmenting a kind of model for certain reason from the legal, the administrative, or any other point, it is through inference, similarities, and all those kind of things that will try to align that model to understand what democracy is and if America truly is a democracy. Because if we go by fact, grounded, you will not see that information in any of the official documents. I mean, from the founding principles up to some period. But at some point, they start inferring and that alignment. So if we look at vectorizations, all these kind of semantic similarity, bringing in the kind of contextual learning, all to kind of understand hermeneutics of a text, then we can now start approaching like the first kind of inference that the first question was saying. So my own question now really like be, to what extent, if we have to rely on the model, to what extent can we be sure that what the outcome of the model is given is based on inferred or grounded fact? Because we do not see. Yeah.
So there's actually like, this is a whole different area that people are working on. So in tools like Gemini or Bing, they have this problem of like adding citations. Like, can we show the correct link from like, for this claim, where did I get this information from? So there's been a whole lot of work about how to map this, like the generated content versus the claims. Is it coming from the vector database retrieved information or from the weights of the model? So there's a whole different set of papers that I can share with you, like keeping this grounded and keeping this factual. So in this case, I was mostly talking about this grounded nature. But keeping it factual or keeping it like applicable to like the general laws of the world, that's a whole different problem that folks folks offering search engines or that type of things that we have to deal with. So RAG is a specific solution for a specific problem, that is, if model doesn't know about certain things because it's private or because it's recently happened, how can we push this information into the model without going through the whole path of retraining from scratch or fine-tuning. So it's like a cost-effective approach of answering a certain question. But if you are to think about, okay, adding citations or keeping it factual, so that's a whole different problem that researchers are looking into, but I didn't cover that in this talk. Yeah.
Let's thank Keheliya for the great talk there.
Thank you.